Okay, general picture of a transformation. Of a linear transformation of T from a vector space V, hate to smudge things, to a vector space W. Okay? And I'm going to assume that V equals Rn, W equals Rm. Okay? That would be defined by an M by N matrix A, so that T of V equals A times the V vector. Okay? Now, if I want to draw a picture of that transformation, I'm not going to try to draw an R2 or an R3. I'm just going to make a big blob here. That could be R whatever. This is our V space. And I'm going to have another blob over here. It's my W space. Then I look for my colored chalk. Okay, because I want to kind of color code some of this stuff. That ought to get me started. Okay. Then I have my zero vector here somewhere in V. And I have my zero vector somewhere here in W. Then I have some subspace of V that consists of vectors that map to the zero vector in W. Okay? So this is what I've been calling the null space. And that null space all maps on to the zero vector. Everything in the null space goes to the zero vector. Okay? Then I have my row space and my column space. Okay, well, let's start with the column space. The column space in W consists of all the vectors that we get from V. We know that that's what the column space is, and hopefully we understand why. So the column space would be this, and then we have parts of W that maybe aren't mapped onto anything. If there are parts of W that aren't in the column space, then there's nothing in V that maps to anything in that part of W. Okay? So we call that the useless part of W maybe, but it's not always useless, so we don't probably want to use that term. Okay? Then we have the row space. Okay? So I'm going to kind of depict the row space like this. And this chalk is, I guess I haven't written with it much, row. Space. Okay, and the row space can be identified with the column space because every point in the row space, or every vector in the row space, goes to some vector in the column space. And also, every vector in the column space came from some vector in the row space. Okay? So that the vectors in the column space are matched one-to-one with the vectors in the row space. Okay? So vectors in column space match 1-to-1 with vectors in the row space. Now, just as before, the vectors in the null space are all orthogonal to every vector in the row space and vice versa. So the row and column space vectors, the row and null space vectors so let's say we have VR, a member of the row space, Vn, a member of the null space, then VR and Vn are orthogonal. VR dot Vn, very simple calculation, make one a row, one a column, and multiply the row by the column, is 0. Okay? So, these are orthogonal subspaces. Now, any vector in V, it doesn't happen to be in Vn, in the null space or in the row space. And, well, let's try it. Here's V. Okay? Well, V is, as before, equal to VR plus a Vn. So if VR is the vector here, because VR stands for a vector in the row space, so let's say here's VR and here's a Vn. Now, I'm not using arrows because these spaces are represented by blobs. I'm representing vectors by points, okay? But if this V equals VR plus Vn, then whatever VR goes to over here, V has to also go. So, VR, I don't have a good room to draw an arrow, but yeah, we can take any path we want. So this is the image of VR. Okay? It's also the image of any V that's equal to VR plus a Vn, where Vn is some vector in the null space. Okay? So for this VR, we add any vector in the null space. This will map also to the same vector. Now, I'm not going to be able to get through all this without crossing some lines, but do it this way. Any VR plus Vn of good there. It's the image of VR plus VN. For any Vn in the null space. VR is this vector, but Vn is any vector in the null space. So there's a fairly good picture of a transformation with the properties that we talked about in terms of R2 and R3, where we actually drew the lines and attempted to draw lines and planes in R3. There's more, but we'll base it on this picture.